Your task in this problem is to factor the expression x squared minus 49. And keep in mind that when you see problems like this in ALEX or on an exam situation or whatever, you won't see like some topical category the way that we had it here, right? It won't say factor or difference of squares in one variable. It'll just say factor, and you'll have to factor an expression like x squared minus 49. So I want you to take a couple of minutes and get the process started of what you would do to factor this expression. And then we'll talk together about how it works, how this is kind of a special situation, but how it's not really that different from what we already learned how to do. So when you look at this expression, x squared minus 49, what, if anything, jumps out at you about the form of that expression? What's important about x squared minus 49? One of the cues that will cue us into being able to use the factoring technique that we're about to talk about is that when we have numbers like 49 that are perfect squares, (49) is a perfect square, meaning that it's equal to 7 squared. Right? And that's the cue that's going to sort of remind us that the technique we're about to use could work in this situation. Because what having a perfect square is going to allow us to do, and here's going to be the connection to ways that we've already learned how to factor. If I'm trying to factor x squared minus 49, having a perfect square in that second entry is going to allow me, if I'm factoring, again, from the inside of the grid to the outside, is going to let me break apart that 49 into a product of a number by itself, a 7 and a 7. So sometimes, and I think this is the way that your ALEX book will kind of encourage you to do this, it'll encourage you to rewrite this as x squared minus 7 squared. To remind yourself that what we really have here is not just one perfect square, but really two. Because the x squared that's out in the front is also a perfect square. Right? It's x times x. So when we go in to break apart the x squared, we can break apart the x squared in the same fashion. An x and an x. Right? So having two perfect squares subtracted from one another, so that's the third bit that I want to draw attention to here. The minus in the middle here. What we would say is that this expression is a difference of two squares. Difference of squares. The squares being x squared and 7 squared, the minus representing the difference. And that minus, the way that we've set up this factoring chart over here, gives us the negative 49 in this cell. So what does that tell us, negative 49, about the 7s that are on the outside of my table that need to multiply together to give me negative 49? What does that mean I should do that I haven't done up here yet? So if I make my 7s both negative, yeah, if I made the 7s both negative, then when I multiplied negative 7 and negative 7, that product would be positive 49. So making them both negative is not, in fact, what we want. What should I do instead? Yeah, we want them to have opposite signs, because that's when a product of two numbers can be negative, is negative, when the two factors have opposite signs. So one of them needs to be negative, the other one needs to be positive. And keeping in mind, if any, what you said last week, it doesn't matter which one I make positive and which one I make negative, because it's just going to change the order of my two factors, which doesn't matter in my final answer. So I'm just going to choose to make the one on the top row negative and the one down the first column positive. Okay, so that accounts for the x squared and the minus 49, but we should be careful, because what we've so far set up for ourselves is what answer? X squared minus 49 equals, how would I write my answer so far? For my first row, I'm going to get this factor of x minus 7. From the first column, I'm going to get a factor of x plus 7. But I'm being a little bit dicey, because we have two more squares in my grid that we haven't accounted for yet. This one and that one, right? So we should make sure that those squares in my grid aren't going to throw us off. So let's complete the grid. In the upper right-hand cell, what do I get? when I multiply from the outside in. Negative 7 from the first row and an x from the first column. In the bottom left, I'm going to multiply the x from the first row and the 7 from the first column and get a 7x. So we should make sure that if I were to re-multiply out this product, x minus 7 times x plus 7, that we don't get something extra, because in principle we might from that top right and bottom left part of our grid. But in fact, what happens when I add these all together? My x squared is going to survive because there's nothing. Likewise, my minus 49 is going to survive because there's nothing to combine with it. But my other terms are going to carry through. I'm going to get a minus 7x from the top right and a plus 7x from the bottom left. And what happens to those? They cancel each other. They have equal and opposite coefficients, so that when we add them together, we get plus 0x, and they cancel. And so that's what makes this method work. This method works because we end up with these two equal and opposite coefficients that when we add them back together, they cancel each other back out. So that's the sense in which this factoring method really was just a shadow of the same factoring method that we used a week ago. That we can use the same strategy to work from the inside of our table to the outside. Another way to look at it, if we wanted to really connect it with what we did last week, we would look for a pair of numbers which multiply together to give me 49, actually negative 49, right? But which add together to give me how much? We don't have an x coefficient here in this part of the equation. So what is the coefficient in front of the x really? It's even better than 1. 0. We don't have any x's at all, any x to the first powers at all in our original expression. So when I add my two numbers together, I need to get 0. And so when you play the game of sums and products that we play when we factor trinomials, we end up asking ourselves, what two numbers multiply together to give me negative 49, but add together to give me 0? And knowing that those two numbers add together to give me 0 means that they have to be equal and opposite to one another, which is what makes this whole thing work. So that I shouldn't just pick any two numbers that multiply together to negative 49. I should pick the numbers which are equal and opposite to one another, 7 and negative 7. And that gave me the factorization that we were looking for here. So this is an example of a kind of problem that if you're on cruise control in an exam, you might not remember that there's something to be done here, right? That x squared minus 49 factors in a way that looks kind of special, right? Because we started with something that's not really a trinomial. It doesn't have 3 terms. It only has 2. And yet, we can still use the same techniques that we did for trinomials to break it apart into its 2 factors. Just remembering that that middle term is secret. It's hidden. It has a 0 coefficient, which is why the sum of the two numbers that we get when we play the sum and product game has to come out to 0. So factoring a difference of 2 squares always follows the same pattern, where we end up with multiplication of the difference of the 2 square roots multiplied by the sum of the 2 square roots.